Today we're going to talk about finding inverses graphically. By the end of this lesson, you'll be able to graph the inverse of a function as a reflection over the line y equals x. So let's start with a few definitions and explanations. In math, the inverse of a function undoes the original function. For example, to undo adding 3, we would subtract 3. To undo dividing by 2, we would multiply by 2. So in Algebra 1, you probably talked a little bit about a function machine. You put a number into the function machine and you get a different number out. So when we're talking about inverses, the thing that was the output is now the input. Or in other words, the x and the y switch. So we're going to take a look at a couple of examples. We're going to make t-charts, graph the original function, make the inverse, and compare them. So I have this shape on a graph. This is not an equation you could write, or not a graph you could write an equation for, but we can still find the inverse of it. So I'm going to pick a couple key points on this original graph that will help me find the inverse. So I'm going to pick the endpoints and the corner points, and I'm going to list them in my t-chart. So that first point is -3, -4. The next point will be -2, +3. Then I've got 1, 3, and 4, -1. To graph the inverse, we already said we switch the x and the y's. So I'm going to switch all the x's and all the y's. Now, I'm going to graph these points. So I'm going to graph the point -4, -3, -3, -2, 3, 1, and -1, 4. Now when I connect these points, I need to connect them in the order that I graphed them. So I started at -4, -3, then graphed 3, -2, 3, 1, and -1, 4. So that is going to be my inverse graph, or the graph of my inverse function. It's a little weird because it's not a normal looking graph, but we'll take a look at a normal one in a second. Here, we're given an equation, y equals 1/2 x plus 1. For the original function, I'm given several x values, so I'm going to plug those into the equation and find my y values. So if I plug -2 in, -2 times 1/2 is -1, plus 1 is 0. If I plug -1 in, I get -1/2 plus 1, which is 1/2. If I plug 0 in, I get 1. If I plug 1 in, I get 1.5. And if I plug 2 in, I get 2. So I'm going to plot those points. And graph my line. Now, hopefully you remember how to graph lines from Algebra 1, so you didn't necessarily need to make that t-chart to graph this line, but I just want you to make the t-chart so we can see how to find the inverse. So just like on the last example, I'm going to switch the x's and the y's. and then I'm going to graph those points. So I have 0, -2, 0.5, -1, 1, 0, 1.51, and 2, 2. There we go. So, what kind of things do you notice about these two graphs that we've looked at? Take a moment and write down your observations. Let's continue with some definitions. Hopefully in Algebra 1 you remember talking about functions. A function is when each input has only one output, or each x has only one y. Oops. We can look at a graph and figure out if it's a function by using the vertical line test. So I'm going to go back to the graphs on the front of the notes and determine if the original is a function and if the inverse is a function. So for the vertical line test, if you hold your pencil vertically, you're looking and seeing if your pencil ever goes through the graph twice. So for example, I'm going to draw a line on this graph. If I draw a line here, I drew a vertical line. This line crosses the inverse function at 2 points. That means that when x is 2, that there are two different y values for that one x value. So the inverse is not a function. But if you slide your vertical line or your pencil across the graph, you'll see that it never goes through the original function more than once. So the original is a function. So on graph 1, the function, the original, is a function. Whoops. The inverse is not a function. If we look at graph 2, oops, we do the vertical line test again. Hold your pencil or draw a vertical line. You'll see that both the inverse and the original are functions because your vertical line never goes through the graph more than once. Now, let's do one more example. I want you to graph x equals 2. If you think back to Algebra 1, when you talked about Hoy Vux, remember that a vertical line has an undefined slope and is x equals a number. So this is going to be a vertical line at 2. So if I pick 2 points on this graph, and I switch the x's and the y's, so I took the point 2, 3, I'm going to switch it to be 3, 2, and I took the point 2, -1, I'm going to switch it to be -1, 2, and I connect those dots, I'm going to end up with a horizontal line at 2 as my inverse. So this is a horizontal line at 2. And again, thinking back to Algebra 1 and Hoy-Vux, remember that horizontal lines have a slope of 0 and our y equals a number, so this graph is the line y equals 2. So we're going to use this idea to find a test that will predict whether an inverse is a function. So I had the vertical line test to determine if a graph is a function. I can use the horizontal line test to figure out if its inverse will be a function. So I'm going to scroll back to the previous graphs and show you what I mean. If I draw a horizontal line, I can see that this horizontal line crosses my original function in two places, which means that its inverse will not be a function, which is what we already determined. Looking at this second graph, if I draw a horizontal line, no matter where I draw my horizontal line, it will never intersect the original graph, which is the red line, in more than one place, which means that the inverse will be a function. So, one more thing to look at. We have said that to graph an inverse, you switch x and y. But there's another way to figure out the inverses. I'm going to go back and graph the line y equals x on all of my graphs. If you remember from your parent functions notes, the graph or the line y equals x is a diagonal linear equation that goes through the origin and has a slope of 1. So I'm going to draw this line on all three of the graphs I've done. And it asks you to look at the graphs and see what you notice. So let's go back and look. If you look at this first graph, you can see that all three of these lines intersect here and here. And if you look closely, you can also see that the diagonal line cuts the picture in half. So let's see if that's true of the other graphs. All of the lines intersect at the point 2, 2, and the purple line seems to go right in the middle of the blue line and the red line. Same thing here. All of the lines meet at the point 2, 2, and the purple line cuts the red line and the blue line in half, or goes through the middle of the two graphs. So, how can we find the graph of the inverse of a function without listing coordinates and switching the x and y's? You can reflect the graph over the line y equals x. So if you're a more visual person and you can see how to just flip this red line over the purple line and end up with the blue line, that's great. If you prefer tables and you would rather list out the xy coordinates and switch them, that's fine, as long as you understand that you can switch xy coordinates or you can reflect the graph over the line y equals x.